Hello everyone, welcome to my talk about our project for cryo-ET reconstruction and visualization, which was a collaboration between the Visual Computing Center at KAUST and the School of Life Sciences at Tsinghua University. Cryogenic electron tomography, or cryo-ET, consists of acquiring a series of 2D projection images of samples under cryogenic conditions at several tilt angles. This set of projections is often called a tilt series, and it's used to create a 3D volumetric representation of the sample using tomographic reconstruction. The main advantage of cryo-ET over similar techniques is that it provides nanometer scale details of the samples in its native environment. However, cryo-ET comes with several limitations. First, in order to avoid sample damage, total beam exposure must be minimized. For this reason, images are taken sparsely and with low beam intensity, producing tilt series with few projection images which are noisy and with low contrast, like the one on the slide. Moreover, due to physical limitations of the setup, the maximum tilt angle is usually 70 degrees, which produces the missing wedge problem. This image corresponds to a slice of the Fourier transform of a reconstruction, and we can see a clear missing wedge of information which corresponds to the missing projections at higher tilt angles. Therefore, standard reconstruction techniques produce noisy volumes with artifacts. These volumes are hard to visualize, as we see in the top image, which corresponds to a 3D visualization of a hard reconstruction. For comparison, the image below is a 3D visualization of a reconstruction of the same data using our framework. Now, let's see a typical cryo-ET pipeline. It starts with the acquisition and pre-processing of the tilt series, which is used to create a 3D volume through tomographic reconstruction. Finally, denoising techniques are applied in order to obtain tomograms that can be used by the domain experts. Regarding the state-of-the-art of cryo-ET reconstruction, first we have the algebraic reconstruction technique and two techniques derived from it, the simultaneous iterative reconstruction technique and the simultaneous algebraic reconstruction technique. Filtered back projection can be used too, but is not recommended due to the missing wedge problem. Finally, we have the model-based iterative reconstruction, which uses probabilistic models for the prior and noise to create reconstructions. Before reconstruction, alignment and other pre-processing steps must be performed. IMOD includes the necessary pre-processing techniques. And after reconstruction, a common technique is subtomogram averaging, but this one is manual and time-consuming. There are also some automatic refinement tools like ISONET, which is a deep learning tool that may remove missing wedge artifacts for low-resolution tomograms. Now, let's see where our framework fits in the pipeline. We propose a GPU-accelerated framework for integrated reconstruction and denoising. The framework takes pre-processed tilt series as input and produces high-fidelity denoised tomograms that can be visualized directly. Let's see the most important details in our framework. The starting point are the original projections, and the goal is to create a reconstructed volume that matches these projections. For this, we use the operator W to create forward projections from the reconstructed volume and compare these with the original projections. In this way, we want to find a reconstructed volume that minimizes the difference between the forward and original projections. Finally, we introduce the denoising term gamma of k times x to regularize this ill-posed problem. Here, x is the volume, k is a matrix, and gamma is a nonlinear function. Gamma and k depend on the selected denoising method. For later reference, we will define the data fidelity term and denoising term. To solve the proposed minimization, we used proximal algorithms, in which the idea is to split the optimization problem into sub-problems, which are solved using proximal operators. Then, proximal operators are combined into proximal algorithms to solve the complete optimization problem. For example, assume that we have the proximal operators A and B for our data fidelity term and denoising term. The pseudocode on the right is a simplified view of a proximal algorithm that would use these operators to solve our proposed minimization. Now, let's see some details about proximal operators. Imagine that we have a function h that we want to minimize. For illustration, the thin black lines are level curves of h, and the thick black line indicates the boundary of its domain. The proximal operator of H is defined as this convex minimization. The term on the right is called proximity term, and it ensures that the proximal operator is strongly convex minimization. This operator finds a point X that minimizes H and stays close to the input point U. For example, if we apply the proximal operator to the blue points, we will get the red points. This movement is a controlled step towards the minimum, and the size of this step is controlled by the parameter lambda in the proximity term. For our framework, first we need the proximal operator for our data fidelity term, which we solved using SART. The proximal operator for SART was derived by applying the definition of proximal operator to the SART formulas. This operator can be easily adapted for other art variations, like CERT. For our denoisers, first we have total variation, which is simply the L1 norm of the gradient magnitude. The proximal operator of the L1 norm is the soft thresholding function, which shrinks the gradients after each iteration. Also, we use non-local means since it resembles subtomogram averaging. Now, let's see some of the results presented in the paper. The leftmost image corresponds to an unregularized reconstruction, and as expected, the results are noisy. In the middle, we have an intermediate result of a TV regularized reconstruction. We can already notice sharper features. The image on the right was obtained with TV and non-local mean regularization, which was applied during the final iterations. The noise is reduced even more without significantly distorting the interesting features. This is a comparison with IMOD and ISONET. As expected, IMOD's results are noisy. ISONET managed to increase the contrast for volumes with low resolution as suggested by the authors. However, it presents only a slightly better contrast and the same noise than IMOD at high resolution volumes. Our method achieved better contrast and significantly less noise. This is a comparison between MBIR and our framework. The results are very similar, which is good and expected given the similarities between the techniques. Finally, this dataset was very interesting because it presents a particular repetitive structure which is perfect for non-local means. The results present great contrast and well-defined features, leading to nice 3D visualizations. Now, let's have a look at the time required to obtain results with different methods. With IMOD, it takes up to 27 minutes to achieve basic reconstructions. ISONET uses IMOD results, and it can take up to 8 hours of extra processing using a B100 GPU. MBIR produces denoised tomograms in a total of 4 hours and 30 minutes using the recommended settings, and our framework requires 28 minutes to achieve denoised tomograms using a B100 GPU. In short, we presented an integrated reconstruction and denoising cryo-ET framework which is robust and flexible thanks to the power of proximal algorithms. The framework includes several reconstruction and denoising techniques, and GPU acceleration enables fast reconstruction times. Thank you.